Hi, this is Professor Fernandez, and in this video, we're going to work through an example of calculating the volume of a solid of revolution using the washer method. This example comes from the lesson notes for lesson 29 in this Calc 2 course. You'll find those notes on this website along with these other resources. So the first thing I will encourage you to do is take a look at the video that preceded this one, video 29.1. Because in that video, I was talking about volumes using the disk method, and in particular about how to do that when the axis you're revolving around is not the x-axis. You can see just if you have paused the video to just read the example, or if you just look at this picture, you can see that in this example, we're going to be revolving around y equals -3, therefore not the x-axis, right? So we're going to use concepts and approaches and techniques from that video. So have a look at that if you haven't already. Okay, so let's dive into this particular example. Again, I won't read through this text. You can read through that. But long story short, we want to calculate the volume of this solid, which looks like a ring. And how is this solid generated? Well, we have this region here between the graphs of g of x is 4 minus x squared and f of x is x squared plus 2. Bounded by -1 and 1 for x. So we have that region, and we're going to take that region, revolve it around the x-axis, around y equals -3, to generate this, if you take just this little segment between those two graphs, you generate this annulus, right? This kind of region between two disks. And as we move around from x equals -1 to 1, we generate this solid on the right-hand side, the ring. So how are we going to find the volume of that solid? Well, first of all, let me take this picture and kind of redraw it, right? And here is y equals -3. Up here is the x-axis. And if I were to draw the region that this region over here that we're going to revolve from -1 to 1, right? This is kind of, let's see, g of x is up here, and then f of x is down here, okay? Now let's pretend that we're just looking at f of x, right? If we just looked at f of x and we were going to revolve f of x around this horizontal line y equals -3, right? We would get this giant region that would kind of be like a, I don't know, like a tire, right? We get a volume like that. So all of this would be filled in that volume. So that's one solid that I want you to keep in mind. This kind of tire solid, where this top one is the function g of x equals 4 minus x squared. To find the volume of that, what would we do? Well, this goes back to video 29.1. We would go in here and we would find the radius, right? From the axis of revolution all the way up to the function, what would the radius r there be? Let me call that capital R. And the radius would be, well, we're 3 units below the x-axis, so this much is 3. And then from here up to the function, well, that's the y value, and this is g of x is 4 minus x squared. So the radius r would be this plus 3. And that's kind of what you see up here, right? The outer radius, we'll call it outer radius, would be 4 minus x squared plus 3. Okay, so that would be what we would carry over here. We'd say, oh, this is pi integral of 4 minus x squared plus 3 dx. And again, we're finding the volume of this solid, pretending that we're going to do that. We would integrate from the leftmost region, leftmost bound for x, to the rightmost bound for x, so -1 to 1. Okay, so that would be the volume of this blue tire, right? So now if we go back and I imagine not doing that. So I'm going to try to erase as much as I can without erasing the things that I do want to erase, but just won't work. Okay, if I imagine now going back and trying to find the volume of the same thing, but instead looking at the volume of the inner portion, right? So I'm not now looking at the volume of this blue tire, but now I'm looking at the volume of the green f of x function, right? So here's the green f of x function. That is this portion. So f of x here is x squared plus 2. What if I revolve that around the horizontal line, -3? Well, it'd be like a very similar thing, right? Let's look at what it would look like. So here would be the radius. Let's call that little r. And I would revolve that around to get a disk. So I would get something like this. right? And then the solid would come up. So I would get, I don't know, I guess I'll call this a tire. It's not quite a tire. It's a very strange looking tire, but I get this solid, right? So our original solid had volume V. That was kind of the tire that looked like that, right? There you go, volume of that. And then now this volume that we just got is going to be pi integral, again, from -1 to 1. Let's figure out this function. Well, to figure out that function, we go back over here and we would find this radius. And the radius from here to here is, again, 3 units below, so that's 3, plus the y value from the x-axis to the function. This is the function, so that's x squared plus 2. So it's x squared plus 2 plus 3. So I go back over here, and this would be x squared plus 2 plus 3. Okay? So now that would give me the volume of this solid. And you can kind of see what's going to happen now, right? To find the volume of the ring, we're going to take the volume here and subtract the volume here. So if I declutter things here so we have enough to look at, a lot more space to do our calculations, we can say that this volume is going to be pi integral from -1 to 1 of this function, which is 4 plus 3, that's 7. So we have 7, and I should have said earlier, this is pi f of x squared, so there should be a squared over here. So I forgot that portion, but we've added it in now here. So this is 4 plus 3, that's 7. So 7 minus x squared. That would be the contribution from here. That's the bigger volume. Remember, that's the actual tire volume, this one. And then minus this volume, which is the one that's kind of like the, not quite a tire, a minus, this is over here, x squared plus 5. And then each of these, again, is being squared. So I get that minus that squared dx. And from here, it's just a question of evaluating the integrals, right? So probably the best thing to do here would be to square this out, to square that out, subtract, integrate using the integral version of the power rule, and eventually, after lots of algebra, right, you'll end up getting 32 pi. But the focus of what I want to do, and certainly what I've been doing in the video, is again to remind you of how you do this. So this washer method, right, and especially when you have an axis of revolution that's not the x-axis, you can again think of it in this way in terms of an annulus. From what we had talked about before with the disk method, right, if this is A and B and you revolve around the x-axis, you pick some horizontal line segment, that becomes a disk, right, whose area is pi, and if this is the radius, in this case, the function f of x, whose area is pi f of x squared. And the volume is therefore integrating that from A to B dx. So what changes over here, and we saw that in this example, and it's really what I want you to take away, is that, first of all, in these washer type problems, you have two functions. So that's really what this line segment is meant to indicate here. And then second of all, you're revolving around the function, horizontal line that is not the x-axis. But you treat them in exactly the same way. So if we step back here, if you look at the volume for this, it ended up being integral from A to B of pi times the outer radius squared minus the inner radius squared, right? So that ended up being what we just did. And therefore, to find the outer radius, we would go here and be like, oh, what is the furthest away from the axis of revolution that the function gets? That's capital R. That's the outer radius. That is 3 plus the y value to here, and this is the function g of x. So that's outer radius R of 4 minus x squared plus 3. Then we go back and we find the inner radius, the closest that the region gets to the axis of revolution. That's from here to this function. And again, that's 3 plus this y value. And what is this y value? That is on the function f of x. So the inner radius is f of x plus 2 plus 3. And then if you go back then, if you go back then and compare what we had written a few minutes ago, right, you'll see that if you plug in this r into here, you plug in this little r into here, it's exactly the integral that we ended up with a few minutes ago. So this is kind of a general formula and a general, hopefully, way to use it in practice in terms of going back to this example to see how it's done. This is a general formula for how to use this washer method to find the volumes, even when the axis of revolution is not the x-axis. Thanks for watching.